Hello everyone and welcome to our discussion of advanced regression models, which centers in Module 5. We'll go ahead and jump straight in. So in this module we're talking about applying advanced regression models for the purpose of forecasting. So the idea here is taking a look at what we've seen in the past and trying to figure out what the future might hold. And then at the end of this module, hopefully you're able to evaluate the principles of advanced regression modeling, develop a generalized linear regression model in one or more appropriate programming language or environment, and then be able to interpret those results of a regression model. So to be able to speak to what it means and what is the outcome. So a little bit of a review first before we get into that, because this type of data that we're talking about typically is centered on time series data. So it's important to kind of take a step back and what are the types of data that we may be seeing. Cross-sectional is kind of the first broad bucket, and this is data that is captured where time really doesn't matter. For example, SAT scores of high school students for a given year. So you don't really care that, what Alan did at 102 whenever I completed a portion of the SAT. You look at the entire thing, right? So it's probably one of the more common types of data that we look at. Another type is the time series, which is what we care about here. And this is data that is captured where time changes, and the time changes matter. For example, here is military spending by year from 1970 to present at an increment of likely year, right? So the year matters. What happened in 2000 versus what happened in 2020 are distinct, and what makes them distinct is when they happened, and that's the key distinction with time series. And then the last type is panel, and it's kind of an interesting, you may hear the term longitudinal study, and that basically is what we're talking about, where you're looking at the example being multiple years, so from 1970 to present, but also considering multiple countries. So it's a combination of not just one series across time, but multiple series across time. And it's captured potentially from multiple sources as well over time. And a panel could be quite useful for figuring out something much more interesting, because you have multiple factors to consider, multiple variables. So those are kind of the types, high level. So digging in on time series characteristics. So what makes time series and what are the characteristics that go with them? You'll hear the term general trend, and that's where something is trending upwards or trending downwards. And that basically means while there may be ups and downs along the way, there might even be cycles involved or seasonality, which we'll get to in a moment. The overall kind of direction of the data, you could draw a line if you really wanted to, and you could see that it basically centers around that line. And generally speaking, that line isn't flat, right? Although that could be technically a trend of no trend, right? Or no change. But it more likely than not is going up or down. So energy consumption in California is likely trending upward over time as population increases and more energy consuming devices come on. Maybe not, who knows? But generally speaking, salaries increase over time in part due to inflation. So there are some general trends. There are obviously some variances in that. There's ups and downs and so on, but you can tell the basic pattern, and that's what is distinct. Seasonality is there's like a cycle involved. So think sales near Christmas, right? So if you were to be a retailer, as a general rule, your sales are going to be higher prior to Christmas than they are after Christmas, and there's likely a peak in there, and then things go back down. There may be little blips here and there, and segments that are also cyclic in nature. They may center around holidays. They may center on events like back to school. They may center on holidays, 4th of July, or who knows. But there's a seasonality. There's also something which is a cyclical movement, and the key distinction between seasonality and cyclical movements is that they're observed after a few units of times, but they don't happen nearly as frequently as seasonality. Seasonality, generally speaking, multiple cycles per year, at least one, it could be multiple. Cyclic could be a solar flare that happens over the span of 20 years or something. And even that could be up for interpretation. And there's always going to be unexpected variations. Things will happen that the previous three sort of things we talked about just can't accommodate for. There are random events that occur. No one could have predicted the COVID outbreak and the impact it would have on our culture. I was speaking with a data scientist that was interested in some work that we ended up not being too interested in. But what he had said was very true, which is 2021 and 2020 were a data scientist's nightmare because things like prediction based upon historical norms just flew out the window. Absolutely meaningless to know what happened over the past 20 or 40 years because it was a totally different sort of environment. A totally new thing happened. So that's where there are always going to be unexpected variations, and we'll see some of those in a little bit. So the next thing that we kind of talk about here is a little bit around autoregressive models. And simply interpreting it, because it may mean a certain thing, but generally speaking, it's about using historical values to predict the future using the same series. So you take a look at what has happened in the past across some set of data, and then you try to figure out what's going to happen in the future. And the way you kind of do that is you take the historical data, you essentially come up with a way of essentially training your model, and then you predict the model over the same period, and then you compare the two things to see how close you got. It's used when there are no other known inputs, and that's because if you look at kind of the definition of some of the things we try not to do in data science, this is exactly it. We spend a lot of time separating our testing and our training data, right? It's essential that we don't train and then test with the same data as a general rule. This breaks that rule. And the reason being is there's no other alternative. And the reason we do that is sometimes things like science, where we're predicting sunspots and solar radiation and activity. The reason we might want to predict those sort of things is sometimes they cause us grief. They may mess up electronics and various other things. And certainly if you were an astronaut on the space station, you would probably care when they're going to be happening. Finance is a classic example of whenever we try to do autoregressive, because you may have some other factors over time, but it's all looking back at the past, trying to predict the future. And things are potentially going to be a bit murky at best. So with that, we've talked a bit about the various types, and so we'll spend some time looking at some code and actually work our way through it. We'll start with the example of the passengers on an airline in Python. And so I'll go ahead and restart my kernel and clear the output so it's a little more exciting as we reveal things, right? First bit of code here doesn't do anything other than figure out where my home directory is, depending upon if I'm running inside of Linux or inside of Windows. You can see here I'm running inside of WSL2. And kind of a reason for that, but it's becoming a little less relevant sometimes. So anyway, autoregressive models, time series analysis, right? Just talked about that. You can read multiple books on time series analysis, especially if you're interested in finance. So you look at those two things, time series analysis and finance, and there's a lot of people that are trying to make money by being able to predict what's happened, or it's going to happen in the future based upon what's happened in the past. The data sets are oftentimes relatively small. They may be changing by things external to the data set, so you don't necessarily have a way to do it. And that's why you don't have a good set of data potentially trying to triangulate all the possible things that can make things happen. That's when you go to something that's autoregressive in nature. The autoregressive uses the prior known values to predict the future. So that's the kind of basic definition. But you think about it, that's just regression using the data that you've used before, right, or seen before. You use it whenever you don't have a lot of other choice. That's what it comes down to. And again, sunspots, stock prices, and so on. So here is a New York, we're taking a New York charter airline is the example. And we're going to try to figure out weekly passenger data from years 2000 to 2005. We start off with the typical sort of stuff of pulling in NumPy, Pandas, Matplotlib, and we also pull in stats models .api to do some of the actual work. We'll probably take a look at that here in a moment because I'll go ahead and pop that open because it's kind of an interesting sort of thing to look at. And again, this example is taken directly out of the course materials. So this isn't Alan making up stuff. This is what the course designers chose to use to explain this sort of concept to the students. So we start off by reading the file in, and it is in my inside of Module 5's folder, and I loaded it into a Pandas data frame, and so we can take a look at what it looks like, right? And you'll see there those lag values, and those are basically calculating the lag over a previous set of days. There are other models that can be used to essentially determine those for you. We'll look at one of those in a moment. But lag is kind of a common thing that you do over time series analysis. One of the, I guess another example of that is if you do something like stream processing inside of a big data environment, you generally want to consider lag, and it's a way of essentially looking backwards, right? So it's literally that is what is the record before me, or what is the record looking forward potentially, if there's times you actually can kind of do that. But the basic idea is lag 1 is the previous record, and you can kind of see the line here, right? Then lag 2 is 2 records up, and lag 53 is 53 records up, right? So that's the basic idea. And this allows us to take a look at a record that contains essentially kind of a snapshot in time of all the previous records. Again, there are methods that can do that for you, but because of what we're using to do here is what we're doing, and these are in weeks, and this is 53 weeks prior. So that's what those are coming down to. We also want to get rid of all these not a numbers, right, because they aren't really adding anything value to us. So we're going to go ahead and drop them in the next line. And so this is giving us a set of data that is essentially a full set of data across that window. And then we can take a look at, just for fun, switch too many languages. So we can take a look at the first 5 records or so and say, yeah, we did indeed get rid of the first 52-ish, counting from 0, 53 even, records, so that we start off with a full data record, or data frame with a full set of data. So the next step is what we generally do whenever we're doing any kind of machine learning stuff. We separate into 2 sets. We got your target, and you've got your variables. So we can go ahead and do that, and then remove some values that aren't necessarily all that helpful from the data frames. X and passenger kind of become less relevant because it's all about now the lag, and we kind of can figure out relative to this what the others were. And so you can get rid of it, and so then we can take a quick look at what's in Y, targets that we're looking for. Oh, that's right. We move passenger from here because it's in the other one, right? So we actually, our Y is what we're trying to get. That is our target, so we don't want that in X. Then, again, take a look at X. Should be basically everything but just the indexes and the lag values. So the next thing is going to be using a OLS model, so ordinary least squares model, to do the prediction. Again, this is an interesting choice, but it seems to work reasonably well. The stats models is a set of, you guessed it, statistical models. And in particular, the one we're looking at is inside of the namespace of regression. And in fact, it's a linear regression using ordinary least squares. So that's the model that we're using to do this essentially prediction. So then you basically are saying set up the model and then call fit and then take a look at the summary and see how well it did. And then, excuse me, we can take a look at the p-values and lag 5 is not real good, so we probably don't need it. So interestingly, rather than, in this example, rather than removing it, we are recreating essentially by essentially selecting the ones we care about, right? And so the main thing that's missing there is lag 5. So we do the same thing again, do a run, do a summary, and then we can compare the various values. And the coefficients appear to be significant now because we got rid of the one that didn't necessarily matter. And then we're going to now attempt to predict the passengers for a given week. So we're moving into, we've got the historical value, now we're going to select it plus the date and be able to compare our predictions to what actually happened. So here we're going ahead and running that and getting the prediction of the passengers. And so now we can plot it and take a look and see what does it look like. And you can see did pretty close, and in fact kind of even caught up there around 9/11, right? And that's what's going on with this big, where we're just, you couldn't predict that historically, right? But otherwise it doesn't do too bad. Actually, you can see doing a reasonable job mapping it. Now, does that mean that it could predict something in the future? If something uneventful doesn't occur, or something eventful doesn't occur, then maybe. But you can take a look at that, see that it looks reasonably good, and it's also can predict based upon whatever. And this is essentially, you can see a seasonality. All right, there's definitely seasons here, and you can also see the overall trend is definitely going up because you could draw a line, split the difference, and it actually could probably work out pretty well. But again, you can, this is in that category of that fourth set of data that I talked about of unexpected occurrences, right? There's no way you could predict that that's going to occur. And that's one of the things that makes it challenging for somebody doing data science, is there is a ton of factors in the universe that could affect things, and some of which can be predicted and some of which cannot. The interesting thing to this one is it seemed to catch up pretty quick, though, which is pretty impressive. It didn't catch it going all the way down to almost nothing, right? How could you predict that? But the fact that we're doing the lag sort of estimates, it wasn't like it took it a year to figure it out. So that's pretty cool. So with that, we can switch and take a look at the next one, which is the same thing in R. So I'll close this, switch over to R, and for the big reveal, restart the kernel and clear the output. So we pull in a few libraries, and then we again read a file. Interestingly enough, with the R kernel, it seems as though as long as the notebook and the file are in the same directory and you don't do anything funny about switching your directories, kind of just works. So that's kind of cool and handy. I haven't had that luck with Python. I have to figure it out in Python. So here we're basically creating a model, and again, similar sort of thing is we're creating it, setting up the various values, and getting back the estimates, and then we can create the model without a stepwise selection, and then plot it. And again, a very similar sort of experience, right? So not too bad. So you can again see fairly close, a reasonable sort of approximation. And again, what you're getting at is the cyclic pattern. And from this, you could potentially extrapolate roughly, assuming nothing dramatically changed that impacts the overall trend or the seasonality of when the peak travel times are versus they're not, then it's potentially quite useful. Again, I'm sure if you were to plot this with COVID, it would be pretty interesting as well, especially because it has been a long-running sort of thing, right? So the next thing we'll talk about is looking at an actual auto-regressive model. Actual meaning that it's really part of, that's what its name is. So go ahead and restart the kernel and run again. This is based, and I'm not taking credit, this is this guy's work. I just got it into a notebook so that we could look at it. Pretty good article, autoregressive-AR models with Python examples. And this goes into what autoregressive models really are, and in particular, the use of the AR model in the stats models namespace. It talks about alternatives to the various models, and this one I saw quite a bit with, it's an autoregressive integrated with a moving average, and you'll also see the summary, a seasonal autoregression integrated moving average. If you take nothing else away from this lecture, take away time series analysis and regression is a thing unto itself. We could have a class on just this, right? And spend every bit of 8 weeks probably getting through the material. So it is its own thing. Not a trivial topic at all. So switching back to my copy of their code, we start off with things as we always do. We import pandas, NumPy, matplotlibs, plotly, or pyplot, and then this is the part that kind of matters, right? We're actually pulling in from stats models an AR model, so we're actually pulling in autoreg, and that's autoregression. So we're then going out and downloading some file from a GitHub's folder of some values, CSV values, reading them, and this is a nice way of doing data with pandas and not having to worry about where are those files, right? I've started doing this on a lot of my stuff, putting the data on a GitHub account that is pretty much publicly accessible. I do that for students in classes sometimes, especially ones that have a history of challenges of getting the data running correctly. And also it's a way of making it really easy to spin something up fairly quickly. Sorry, my phone was going nuts for some reason. So we can now plot the, it's a bunch of Rasmussen notifications, kind of interesting. We can now plot the graph of what it looks like and see this is, I'm assuming, German power consumption over some unit of time. And you can definitely see there's some cycles in there, right? So probably seasonality, and that's probably multiple years. So we can kind of just visually notice some stuff. Then going into, before we start going and actually doing the training, you do some tests to essentially determine if it's appropriate to use this sort of approach, and if so, what sort of lag is appropriate as well. And so we figure that out by doing this essentially a stationary test, I believe is what it's called. So go ahead and run that. It's a partial autocorrelation. That's what it's called. Sorry. And so basically here you can see that once we get around here, that's probably far enough. So 8 is probably good as far as lag goes. So if you do more than 8, it's probably excessive. And so here we can basically create a test and training data, sort of a little better of approach than what we saw in the previous example, because we actually are kind of here trying to see if what we predict based upon the past and what the future is actually going to line up. Some statistics, and then we can go ahead and do the predictions. To me, I look at this and it doesn't look fantastic, right? But it is closer to being real. So the test data is red, so that's the real data. So the blue would be the prediction, right? So prediction, it's catching some of the curve, but it's obviously not really catching it's got the shape but not the magnitude, right? So and in fact it appears to be trying to trend downward, probably because of that huge dip, but isn't really lining up all that great. So again, we use this sort of model and approach because it's what we got to use, right? It's that simple. There are no good alternatives. So yeah, that's part of what this is. So we'll go ahead and save this and then move on to the next one, which this is taken directly from that stats model help page, right? So, and it is the sun activity. And there are some interesting things here, and this again could be something as a talk unto itself for some time, is the various ways of determining how well a model is doing, especially when you start talking about things like time series analysis and things that have interesting distributions. There are these various different values. I'll go ahead and pop that open just so you can see it. But when you're talking about the SIC, HQIC, and AIC, the key thing to take away is you want the littlest value. That's the short, the Cliff Notes version of it. A whole lot more that could go into it as far as determining which is the appropriate, but from a simplistic perspective, lower is better. And so we'll go ahead and step through this. And basically what we're doing here is loading the sunspots data set into a pandas data frame. And we're looking at the sun activity, and we're basically saying these are the things that we're looking to get out. And so we can go ahead and print the first of the lags, of various lags, so 1, 11, and 12, to determine how well that's doing. Then we try it again using some seasonal characteristics on it as well. So we're basically saying we're setting this flag of seasonal equals true and period equals 11. And so we're basically letting it know, hey, we know this is a seasonal sort of data likely, and so we want to see how well it hits. And again, it's not quite as good, right? Because lower is better. These are a little bit higher. So that by itself is not that great. But if we combine those two things together, so you're doing the lags of 1, 11, and 12, and the seasonal is equal to true, and period is equal to 11, and you do the fit, it actually gives us the lower values yet. So lower is good. They're lower on all of them pretty much. This one, yeah, all of them are lower. So if you're assessing which is the better way to go, it's obviously better, right? So that's the gist of that. Moving back to our regularly scheduled programming. Pretty decent book, Practical Time Series Analysis, if you're really into this sort of topic. It's not a light read, so keep that in mind. This is a field unto itself, something that's quite interesting, but also quite challenging. So deliverable 5, something that's near and dear, I'm sure, to everyone's heart. The competency here is to be able to apply an advanced regression model for the purpose of forecasting, similar to what we've been talking about. Again, you're still a data scientist at Frostbite Falls Bank. Your bank's collected a large amount of data regarding the number of new loans originated at the bank over time. Your bank is interested in being able to predict the number of new loans that will originate over the next year. Your manager, Paul Fries, has asked you to analyze the previous data collected and look for trends. Then using that analysis, you need to predict the number of monthly loans over the next period, so over the next year. So your instructions, select one or more of the following programming languages, SAS, Python, R. Mastery is achieved by doing 2 languages or more. So if you want that 4.0 sort of category, then 2 languages. For each programming language, do the following. Create a linear regression model that predicts the number of new loans given the number of loans generated in the past. Keep the model as simple as possible while striving for accuracy. Generate a time series graph that shows the prediction of your model as well as the true values. Discuss whether the graphs are similar. Discuss the model and whether it makes sense from a business standpoint. And then the fourth item there is forecast the monthly loan origination for the next year using the model and Microsoft Excel. So highly data science centric tool, Excel. It's amazing how much we still use it. All right, so what do you submit? A separate text file containing the source for each of the programming languages you use. And it doesn't have to end in .text, although that does make it easier for the .r stuff, but I can download and take a look at it anyway, so don't worry about that. An MS Word document that contains pretty much a write-up as well as screenshots that are used in an appropriate way to bring value to the results. An image of the time series graph showing both the model output as well as the actual data. Some visualizations, a copy of a Microsoft Excel spreadsheet that incorporates one or more model formulas needed to predict monthly loan origination for the upcoming year. So that's new. Generally speaking, you don't have to turn in Excel sheets. This time you do. And then write a memo in Word format to your manager discussing your model, how it predicts future loan origination, present your predicted loan originations for the upcoming year, discuss any observations related to the trends and months that have higher loan origination. So when's the busy time? If there are no trends and months that have higher loan originations, make sure to state this explicitly in your memo. So if it happens to not have any kind of seasonality, that's kind of interesting and it would be worth knowing. We're fairly familiar, I believe, with some of this data. This is new, sort of. It's basically doing the lag for you again, right? So you've got the date, the number of loans from 1 to 12, so from 12 months ago. Should be fairly easy to take what we just saw as far as the code that's available to you in the course room and kind of elaborate what needs to be done. So the rubric, as always, 2 programming languages is multiple, so more than one programming language. You have screenshots that are clear and are well planned and show a full understanding of accurate outputs. Image of the time series graph showing a clear and thorough understanding of both model outputs as well as the actual data. Spreadsheet incorporating model formulas needed to predict monthly loan originations as is accurate, and a clear and thorough discussion of the model and how it predicts future loan origination. Clear and thorough presentation of predicted loan originations for the coming year, and a clear and thorough discussion of observations related to trends and months that have higher loan origination. So is there seasonality? What's the overall trend of the data? Hopefully it's not going down, especially if you work at said Frostbite bank, because down is never good on trends. So with that, we've reached the end of what I have prepared. As always, if you have any questions, do let me know. It's an interesting topic. Again, there's a little bit of a disconnect between the topic of auto-regression and because as you can see, this particular auto-regression, and especially if we take a look here, they're not calculating the lag for you, right? So the data set you've got has been calculated. It makes your life a little easier, right? You could do the same thing yourself, but I believe that's the primary reason that it's being done the way it's being done, is that rather than using a proper auto-reg sort of implementation and functionality, the designers of the course are kind of taking it easy on you, right, and letting you use the ordinary least squares approach to do the estimation of and the fitting. So with that, I'll go ahead and wrap things up. As always, if you have any questions about this material, do let me know. That's what I'm here for. Also, if there are any topics that you want to talk about, let me know that as well, because my plan is to talk about the final module next Thursday, and then start circling around to topics of interest, right, to make this a bit more of an interesting, as it is a fairly senior level course. I mean, we're getting near the end of the program, right? So as it is interesting and compelling, if we can make it interesting, that's fine. Obviously, if there's any questions on any of the previous material, I'll certainly try to give it another go, right? And we can circle back to it. And that's a reasonable expectation, and I may do so anyway to ensure that everybody keeps moving forward. You guys are doing great. You're staying on top of it. You're continuing to make progress. Impressed with that. I appreciate it as well. I hate seeing it whenever students lag to the end and are suddenly trying to get everything in the last week or two, because it usually doesn't go well. But that's not been the case in this course, and I am thankful for that. So as always, stay safe. Let me know what's going on, and I'll speak with you on Thursday.